right. Okay, good. I will start now. Okay, now I'm going to give you a little introduction to something that is often that maybe some of you have never heard of. But as soon as you get into image analysis, this will pop up here and there, and it's quite complicated to find. I found when I was looking for that it was difficult to find a simple explanation to what it is and what we use it for and stuff like this. So I thought I would do the job for you. So here we go. Um, so when we are used to seeing music described this way, so you know, you listen to music and everything, and many of the apps that play music on your phone, they show you the frequencies and the amplitude of the frequencies. So music can be heard. It's a signal that can be heard by our ears, but it can completely be described as frequencies like this, many different frequencies. So the sum of its frequency. And when we consider this frequency, this is just simply two different ways to display the same information. Okay, so this, what you listen to, and these frequencies are actually exactly the same thing. It's just two ways to display this. Each column here represents a frequency, and we have the amplitude as well. There is no difference between the information that you hear, except that, of course, your ear is maybe not very good. That could be, but the information that comes out of and the information that is displayed here. So the information that is registered, let's say when we record this, and this the same information. So we can go back and forth without losing any information. Okay, no information is lost when going from the sound to the frequency representation and back. Well, guess what? It's the same thing with images. And I'm not going to go into the math of the thing or how that works or what. But anyway, an image that is recorded can be completely described as the sum of its frequencies. And so we can go from this image to that one without losing anything. This is a spatial representation of the image, so it's an image, whereas this one is called the Fourier transform representation. So again, it's the same thing. It's two ways to display the same information. And each dot in the Fourier transform, you see there's also little dots everywhere, each dot represents one frequency, but as well as its amplitude, phase, and orientation. And again, I'm not going to go into the details of this. You can find this information everywhere. What I want is that you understand what we do with this thing and what does this represent, okay? So no information is lost between the two representation of the image. We can represent the image in this spatial representation or in the Fourier transform representation, back and forth, going back and forth. We do not lose anything. So I want to tell you what is this Fourier transform doing this and where does it come from? So I remind you that we can manipulate light with lenses and irises, okay? And we have our little points, our little fluorophore here that is fluorescing in all directions, goes to the microscope, and then the lenses are transforming the light, and it's focused in such a way that some here and there we have some intermediate image plane. So we have an image plane here. We have also the final image plane. That's what we are measuring. So this is the way what we have seen before at the beginning of the course. So there are the image planes, and then there is the rest here, right? If we put a sensor here, we measure the image, we record the image. But what happens if we put a sensor where we have no image planes, in between the image planes? Well, that's what we're going to see. We're actually going to record the Fourier transform of the image in these spaces. So we have image planes in the microscope and we have Fourier planes. And the Fourier transforms are not only a way to display image information, like I've shown you, we go back and forth like for sound. It's also something that happens physically inside the microscope. So we have here, let's say that this is our sample. And we have the sample plane here. So we're focused in this point at the sample. And then we have our objective. And we have you can see how the light is diffracted. If you remember well, when the light comes in with a certain angle, then it changes angle. But if the light comes straight, it keeps on going straight. And so the light that is here will end up right spot on in the middle. So we have this representation of the image is exactly the same thing as what we are actually recording. So it's the light that makes it through the microscope is going to be here. So before reaching the image plane, the interference pattern of the light coming from the sample is a Fourier transform of the final image. And the Fourier transform can be visualized when a camera is placed at a Fourier plane. Okay, and there are several of them. Oh, I go the wrong way. The tube lens transform, the Fourier transform in the final image, which is recorded. And the Fourier transform contains all the frequencies emitted by the sample and captured by the objective. So here we go. We have this sample, the objective, Fourier plane in this Fourier space, the tube lens, and then we get the final image. And this is where we put our sensor so that we can record it. So exactly in the same way that we have in the sound display in frequencies, we have on one side the low frequencies, and on the other side we have the high frequencies, where we have the same thing in the Fourier transform. So the low frequencies in the Fourier transform are at the center, and the high frequencies are on the outside. So it's a center to periphery instead of being right and left. It's a center to periphery increase in the frequencies, with the high frequencies being on the outside. So the low contrasted areas in the sample are actually the background area. For example, from here, if I go to this pixel, there's very little contrast. So there's almost no change in intensity. So I see no details in this because of the low contrast. And this is part, for example, the background that you would have over the whole image is also something that is very low contrast. So when we have the low contrasted areas, they have low frequencies that they end up at the center of the Fourier transform, whereas all the edges and dots, like all these edges that are sharp, the letters, the edges of the letters are high frequencies, and they end up at the periphery of the Fourier transform. So what is that thing with sharp edges and high frequencies? So I found this very nice website called askamathematician.com. And this was a very nice way to represent this. So if you remember well, through the microscope, even though, so if we have an image that, a sample that we have is like bands of white and black and white and black. If the bands are very close to each other, we have a high frequency, and then we have a loss of contrast. So there is a transfer of contrast through the microscope that is not 100% at all. It doesn't work so well. So we have, even if we have a sample that has super sharp edges like this, in the image, we're going to have softer edges like that, okay? So we have a loss of contrast, and the image has soft edges. And so this would be our low frequencies that this little guy is showing here. Now, what happens if we have soft edges? Now, what happens if we pile up on top of that a higher frequency? And this is what you can see in here. Now, the higher frequency ends up at the top here. And what happens? This edge here becomes sharper, right? So instead of being so long like this, it's sharper. So when we add higher frequency, we get sharper edges. And we do that again, and we add more frequencies, and we end up with even sharper edges. So the higher the frequencies that we get, and the sharper the edges. And what we are after when we image samples and we want to image dots and edges is that we really want to have high frequencies in the image, so we get super sharp edges, and it's easier to segment our data. Okay, so this is the same thing that I've told you before. An image can actually be represented as a sum of frequencies. This is exactly the background behind the Fourier transform, is that you can completely represent an image as the sum of the frequency. So if the maximum frequency in the image is low, we're going to get soft edges in the image, and it's hardest to segment during image analysis. And what happens in the microscope is that, as I said, we have here our sample, and here we have the Fourier space. Here we have the image planes, and here we have the Fourier space. And in this Fourier space, we have the Fourier transform that is there. But the problem is that the tube, the side of the objectives block the outside of the Fourier transform. And you remember we have the low frequency in the center and the high frequency on the outside. So when we have the objective inner side is chopping off all the high frequencies that we would like to have. And these high frequencies are dots and edges, and therefore that means our image is going to be dimmer. And you can imagine that if we have an objective with because the inner edge of the objective is related to the numerical aperture. If we have an objective that has a smaller numerical aperture, lower numerical aperture, this circle will be even smaller, and we will throw away even more of the high frequencies from the Fourier transform. And this is how it's going to decrease even more the resolution in our image. So the high frequencies, due to this edge, the high frequencies cannot participate to the image at the final plane, and therefore we get soft edges and dots. So the high frequencies are lost. There is a lower resolution, and the light is lost. This is why also we get lower brightness, because we are throwing away all this stuff. And then the inner edge of the objective limits, therefore, the resolution and the brightness, and this is related to the numerical aperture. So this is also the reason why you don't want to do fine microscopy analysis with fluorescence with a phase objective, because in the phase contrast objective, we have a ring inside, and that limits further the brightness for the resolution and brightness for fluorescence. So if you have a very coarse readout of your images, you're fine with a phase objective, phase contrast objective. But if you need fine details, do not use a phase contrast objective for fluorescence because of that extra ring. So why do we care about all this, these Fourier transform? Well, it happens so that representing an image in its frequencies allow more complex and manipulation of the image, and not based on the pixels, but based now on the frequency. So there's a lot more that we can do when we analyze the images if we can use the Fourier transform. So this is an example of an original image that has very fine details, all these microtubules around. And now if I transform this, if I represent this image as its Fourier transform, this is what it looks like, okay? But we have the high frequencies on the outside, the low frequencies in the center. This is the way it is. Now, if I would chop off the low frequencies in the middle, so I cut off this part of the image, and I retransform this new image into my spatial image, what happens? This is what I get. So you can see that in this image, I have only kept the high frequency, and I've removed everything that is considered as background. So all the long variation where from one pixel to another, we have almost nothing, like for example, no difference is here. Then this disappears, and we are left only with the edges. So this is an image where we have only the high frequencies. Now, if I do the opposite and I remove most of the high frequency, I only keep the center where we have the low frequencies, and then I retransform this image, this Fourier transform, I display it as a spatial image. This is what happens. We're getting only the low frequencies. We have all soft edges everywhere, much softer than in here, okay? So using these tricks in the Fourier representation of the image is extremely useful for image analysis. You can do lots of things with the Fourier transform. So if we have the high frequencies in the Fourier transform represent the edges and dots, and the middle frequencies are the big shapes, and the low frequencies are information that has no edges. For example, a blurry background or cytoplasmic stain, things that don't change a lot between one pixel to another, end up in the low frequency at the center. So then we can do all sorts of filtering of one or several frequencies or a range of frequencies. We can filter this out of an image, and this is used a lot in image analysis. So we could do an edge detection, for example. We could remove an uneven background. We could blur the image to make it easier to segment and all these type of things. We will, I think, use some of these on the last module where we do some image analysis. And there are some very nice apps that for the geeks among you, I'm sure we have lots of geeks among you. You can download these apps. Unfortunately, this one is gone from the at least the Google Play thing, but you can download it and install it yourself. And this one you can download from the Google, and it's really nice because then you can choose yourself what is the numerical aperture, what is the magnification, what is the wavelength, and it gives you all the information that you've had to calculate so far in the course. What is the resolution? What is the Z step, etc. So this is a really nice app from so that you can download. Okay, so now I would like to know first if you have any question about the Fourier space and Fourier transform. If anyone has heard of it before. Has no one heard of Fourier transform before?
Yes.
Who was that? Yes.
Moa.
Moa has heard of Fourier transform. Is this the only person who's heard of Fourier transforms before?
No, I've heard, but I'm wondering if I've used it. I think maybe I've used it at one point to downsample images that you can downsample more heavily without losing details by just keeping the low frequency center.
Yes, absolutely. But again, of course, if you have tried some image analysis plugins or tools, it is also possible that it is done in the background without you knowing it. So that the tool would transform things in the Fourier transform and then filter based on something, and then without you really knowing it. So, but the thing is that if you've never done any image analysis, then it's likely that you haven't heard of it. But hopefully now you realize that how useful using the Fourier transform can be when you're doing image analysis, because you can filter out things in a different way that you can do in the space image. So I'm going to use my couple of 3 little minutes that I have now to just tell you what I hope you have learned so far in this course. Just to summarize a little bit, because I want to make sure that you realize the amazing amount of stuff that you have been learning and that you have been using extensively so that you can use now. So I hope that you have learned that how important it is to formulate your scientific question in terms of metrics in the image, something that you need to measure to answer your scientific question, and also that your scientific question has to be adapted to the limitation of microscopy. So you need to be aware of the limitations of the technique so that you have a scientific question that can be answered. I also hope that you have learned that from there, you need to choose the microscope and the resolution setting. So this is the number one thing, and this comes afterwards. So if the scientific question and the image analysis dictate the required resolution in the image, and then we ask ourselves, which microscope technique should I use? Well, fast is good, right? And then which objective? Oh, we would love to have the largest field of view, but sometimes we can't. And then which sampling strategy? So yeah, you know that this comes along. We have to have the optical resolution, but also the digital resolution. And then there again, we would like to go fast. And sometimes we have a certain digital and optical resolution, but we do not need it. So it's also okay to undersample and to not use the full resolution of the objective. It's also okay. And then we have the constraints of our experiments, of course, and our sample. And therefore, sometimes we have to undersample, and we will create aliasing artifacts. And if we undersample in Z, we will miss information. So as long as we are aware of it, and this is something, it's a decision that we can justify, it's totally okay. And you can explain to someone why you've decided to not record all the information, for example, then it's totally fine. But it has to be a conscious decision. And then we need contrast in these images, because even if we have a very high optical and digital resolution, if we have no contrast, we can't use them anyway. So we need to minimize the factors that reduce the analysis reproducibility. So the aberrations like refraction and scattering. So maybe our sample needs clearing, but we need to work on the sample to have a good sample. We need to make sure we have a reproducible focus. And then we work on the setting of the macroscope to have the signal to noise ratio and the signal to background ratio that matches and allows us to answer our scientific question. So, and then we have some artifacts that we know we don't want. One of them is bleed through. The other one is saturation, underexposure, and then the noise and aliasing. So these are things that we can live with as long as our scientific question can be answered. So they should not affect the interpretation of the image in relationship to the scientific question. So I think that hopefully nothing in here is just new to you. And I hope that you understand each of these lines. And I think it's because you have learned so much so far. And so I'm pretty proud of you guys. You've been doing a great job. So this is what I wanted to say. And I want to know if there are any comments or questions for this before we move on. If not, let's go to the other Zoom and we're going to have a little discussion about AI and super resolution. I see you guys there.